Green hydrogen has long been described as the missing piece of the clean energy puzzle. A fuel so versatile it can power industry, transport, and even agriculture. But despite its promise, one stubborn barrier has stood in the way: cost. Producing hydrogen from renewable electricity is still expensive, typically between $4 and $6 per kilogram, far above the $1 to $3 range of fossil-based gray hydrogen. For the global energy transition to succeed, that gap has to close fast. The world has set a collective goal: green hydrogen at $2 per kilogram, a tipping point where it becomes truly competitive with natural gas and industrial hydrogen made from steam reforming. Reaching that milestone will require breakthroughs across the entire value chain, from cheaper renewable power and smarter system integration to more efficient electrolyzers. And among those electrolyzers, one piece of technology has quietly emerged as a major driver of progress: the membrane. Inside every proton exchange membrane, or PIM electrolyzer, a paper-thin polymer sheet acts as the heart of the system. Its job is to separate hydrogen and oxygen gas during electrolysis while allowing only protons to pass through. It's the invisible boundary that keeps the entire process safe, stable, and efficient. But it's also one of the most expensive and failure-prone parts of the stack, and until recently, one of the least sustainable. Traditional PEM membranes are made from perfluorosulfonic acid polymers, such as DuPont's famous Nafion are. They're chemically strong and conduct protons efficiently, but they come with downsides. These materials rely on PFAS, so-called forever chemicals, that don't break down in the environment. They're costly to produce, sensitive to impurities, and tend to degrade under the extreme voltages and temperatures of long-term hydrogen production. Over time, cracks form, contaminants leak, and efficiency drops, forcing operators to replace stacks, driving up operational costs and downtime. That's where next-generation membranes are changing the game. Researchers and companies across the world, from national labs in the US and Europe to private innovators in Asia, are re-engineering the membrane from the ground up. Their goal: create PFAS-free, longer-lasting, higher-efficiency membranes that can withstand industrial operation for tens of thousands of hours while cutting both environmental risk and production cost. These new membranes use hydrocarbon-based ionomers, such as sulfonated polyether ketone, SPEAK, and polybenzimidazole, PBI, instead of fluorinated polymers. Others integrate reinforced composite backbones, embedding fibers like aramid, or expanded PTFE to strengthen mechanical integrity without sacrificing proton conductivity. The results are membranes that can operate at higher temperatures and current densities with less degradation. In short, they make every kilowatt of electricity count. To understand how important this is, remember that electricity accounts for roughly 60 to 70% of the total cost of green hydrogen. If a membrane can reduce the energy required to produce 1 kilogram of hydrogen from, say, 55 kilowatt hours to 45 kilowatt hours, that's a direct 10 to 15% cut in production cost. Combine that with longer stack lifetimes, doubling from around 40,000 hours to more than 80,000 hours, and the economic impact compounds. The same equipment now produces twice as much hydrogen before needing replacement. These are not theoretical numbers. A review published by Hydrogen Newsletter in 2025 highlighted a new generation of membranes that deliver up to 15% higher efficiency, 2 times longer durability, and reduced environmental impact thanks to PFAS-free chemistries. Labs at Rice University and Germany's Fraunhofer ISE are demonstrating stable operation beyond 20,000 hours with minimal performance loss. Meanwhile, companies like 3M, Ballard Power Systems, and various Asian startups are pushing membrane electrode assembly (MEA) designs that combine thinner membranes, as low as 15 microns, with advanced catalyst coatings. So what does this mean in dollars per kilogram? Let's translate it. Today's typical PEM electrolyzer might consume about 55 kilowatt-hours of electricity to make a kilogram of hydrogen. At an average renewable power price of $40 per megawatt hour, that's $2.20 in electricity cost alone. Add stack depreciation, O&M, and balance of plant expenses, and the total levelized cost can easily exceed $4 Now, imagine a next-generation membrane that lowers energy consumption to 45 kilowatt-hours per kilogram, extends stack life, and allows cheaper, non-PFAS materials to be used. The same plant now pays $180 for electricity, and because the stack lasts longer, amortized capex per kilogram falls by another $0.50. Add smaller O&M savings and the total cost drops toward $2.30 to $2.50 per kilogram, almost at parity with fossil hydrogen and well within the reach of that global $2 target once renewable electricity costs decline a bit further. It's easy to underestimate how much a microscopic film can influence billion-dollar energy economics. But membranes sit at the intersection of physics, chemistry, and finance. They determine how efficiently energy moves through the system, and therefore how profitably hydrogen can be produced. The environmental benefits are equally transformative. The move away from PFAS addresses one of the growing contradictions in the green hydrogen narrative. Governments in the European Union and the United States are introducing strict PFAS bans due to groundwater contamination concerns. Without PFAS-free alternatives, electrolyzer manufacturers could face major regulatory hurdles by the late 2020s. By adopting new materials now, developers future-proof their assets and avoid the risk of retrofits or legal liability, an increasingly important factor for investors assessing ESG compliance. There's also the question of supply chain resilience. PFAS precursors are specialty chemicals with limited global suppliers, often located in jurisdictions exposed to trade restrictions. Replacing them with hydrocarbon polymers or ceramics that can be produced locally helps diversify supply chains and stabilize costs. This aligns perfectly with national hydrogen strategies in India, Australia, the EU, and the US, all of which emphasize domestic manufacturing to build competitive advantage. In other words, membrane innovation isn't just a lab breakthrough. It's a strategic industrial policy lever. But to hit $2 per kilogram globally, membrane advances must coincide with progress in other parts of the hydrogen ecosystem. Electricity costs must fall below $25 per megawatt-hour in renewable-rich regions. Electrolyzer factories need to achieve gigawatt-scale production to capture learning curve benefits. And integration technologies, such as AMP's DC-coupled solar-plus battery systems, must ensure that power supply to electrolyzers is smooth and optimized. That's why professionals in this sector increasingly talk about stack-to-system synergy. A more efficient membrane means nothing if the power electronics feeding it are inefficient or intermittent. Conversely, even the best DC optimization won't reach its potential if the electrolyzer stack wastes energy through subpar materials. The $2 goal is achieved when every component on membranes, catalysts, power systems, cooling loops, and offtake pipelines works in harmony. Think of it as the hydrogen equivalent of what happened in the solar industry 15 years ago. Early PV modules were expensive and inefficient until a series of small material and manufacturing improvements, thinner wafers, anti-reflective coatings, better encapsulants, compounded into massive cost drops. The same is now happening in hydrogen. Each incremental improvement, like these membranes, nudges the LCOH downward by a few percentage points. Stack them together and the cumulative effect is transformative. So how does this tie into what we do at h2hub.reneenergy.com? H2Hub is built to bridge that gap between technical innovation and project execution. It's where green hydrogen professionals learn how to turn breakthroughs like next-generation membranes into bankable project designs, financial models, and investment strategies. On the platform, you can explore detailed modules explaining how electrolyzer efficiency, stack lifetime, and capex directly feed into the levelized cost of hydrogen. Our interactive models let you test scenarios. What happens to your project economics when membrane efficiency rises by 10% or when lifetime doubles? The result isn't just theory, it's actionable intelligence for developers, consultants, and financiers. Consider this scenario. You're planning a 50-megawatt hydrogen plant. With today's membrane tech, your modeled LCOH is $3.80 per kilogram. Plug in the data for next-generation membranes. lower power consumption, extended durability, and watch the model drop toward $2 or in 20s. You can then integrate renewable power cost curves, financing assumptions, and offtake pricing to see when your project hits parity with gray hydrogen. That's the kind of decision support H2 Hub is designed to offer. Beyond modeling, the platform also curates case studies of how advanced materials are being deployed in the field. We examine real projects, from the Good Earth Cotton hydrogen ammonia system in Australia to pilot PEM plants in India and Europe, highlighting the specific technology levers that push them closer to 2.1K. Each study links technical variables like membrane performance to financial indicators such as capex per kilowatt and debt service coverage ratio. This knowledge isn't just academic, it's how investors, engineers, and policymakers make confident choices. In a sector where every tenth of a dollar per kilogram matters, understanding the microscopic chemistry of a membrane can change the macroeconomics of an entire project portfolio. Membrane durability also ties directly to financing terms. Lenders and equity investors favor predictable maintenance schedules and long equipment life. A stack guaranteed for 80,000 hours of operation reduces perceived technical risk, which can translate into lower interest rates or longer loan tenors. Cutting the cost of capital, another major driver in achieving the 2 target. On H2 Hub, users can simulate these financial effects in their project finance templates, seeing how technical reliability metrics convert into improved IRR or reduced payback period. Another emerging advantage of advanced membranes is operational flexibility. Modern PFAS-free materials can handle higher current densities and wider temperature ranges, allowing electrolyzers to ramp up and down more dynamically. That makes them ideal for coupling with variable renewable sources like solar and wind. Improved flexibility boosts utilization rates, and in hydrogen economics, utilization is king. A plant that runs 75% of the time instead of 50% spreads fixed costs over more output, further lowering cost per kilogram. In this sense, next-generation membranes are more than a performance upgrade. They're an enabler of system-level optimization. They make it technically feasible to operate hybrid systems where renewables, storage, and hydrogen production are seamlessly integrated. This is precisely the architecture being pioneered in projects worldwide, from Europe's hydrogen valleys to Australia's port hydrogen hubs. There's also a geopolitical dimension. As countries race to secure green hydrogen leadership, control over key materials like membranes becomes a competitive advantage. The shift toward non-PFAS, locally manufacturable polymers allows emerging economies to build domestic electrolyzer industries instead of relying on imports. That means lower supply chain risk and new economic opportunity, both vital for accelerating adoption. Looking ahead, researchers predict that membrane innovation will contribute roughly 20 to 25% of the total cost decline needed to reach $2 per kilogram by 2030. The remaining reductions will come from cheaper renewables, larger factories, and smarter integration. But the membrane is the beating heart of that progress, a small component with outsized impact. At h2hub.reneenergy.com, our mission is to help professionals understand these interconnections. We're building the global knowledge base for developers who want to turn technical potential into financial reality. Whether you're designing a 5-megawatt pilot or a gigawatt-scale facility, our tools and courses show how innovations like advanced membranes translate into lower LCOH, stronger project bankability, and faster path to commercialization. The story of green hydrogen's future may be written in gigawatts and billions, but it starts with microns, the thickness of a membrane. As these next-generation materials move from labs to factories, they represent the kind of incremental yet profound progress that defines every successful energy transition. When you double durability, cut losses, and remove environmental hazards, you don't just improve technology, you reshape economics. So the next time you hear about a hydrogen project touting cost breakthroughs, remember, behind the numbers lies a sheet of polymer no thicker than a human hair, carrying the promise of affordable, scalable, and truly green hydrogen. And if you want to dive deeper, to understand how those membranes fit into the bigger picture of project development, financing, and cost modeling, visit h2hub.reneenergy.com. There you'll find expert-led courses, real-world case studies, and interactive tools that let you model your own pathway to the $2 per kilogram future. Because reaching that goal isn't just about technology, it's about knowledge, collaboration, and smart design. At H2 Hub, that's exactly what we're building. A community of hydrogen professionals turning innovation into impact, one project and one membrane at a time.